The film opens in darkness, not empty but heavy, trembling with invisible tension. A single thread of light bends across the void, curving around something unseen. We are told that every motion, every atom, every thought occurs inside an invisible architecture, one that no one can see, yet all must obey. It is space-time, a silent, flexible web that stretches and folds under the weight of stars. But the narrator asks, what holds this web together? If gravity is only its ripple, what builds the fabric itself? Could the universe be resting on deeper laws, unseen builders, silent architects that shape reality from beneath all known forces? And if so, what are they? Quantum fields? Strings vibrating beyond our perception? Or perhaps something older, a symmetry written before time began? The mystery begins not in the stars, but in the structure that allows stars to exist at all. In the cold winter of 1915, in a small study in Berlin, Albert Einstein sat surrounded by equations that refused to yield for years. He had wrestled with a single question: what is gravity really? For centuries, it had been thought of as a force, a pull that stretched invisibly across the void between planets and stars. But Einstein felt something deeper beneath it, something that wasn't a force at all, but a shape of reality itself. As he worked, he began to see that space and time could not be separate things. They were one continuous entity, a fabric that could stretch, twist and bend. Objects didn't fall because they were pulled, but because the geometry beneath them curved. It was an idea so simple, yet so alien, that it overturned the very foundation of physics. When he finally wrote down the equations of general relativity, the universe itself seemed to take a new breath. Before Einstein, the cosmos had been imagined as a stage, a vast absolute emptiness, where the drama of motion unfolded under the watch of Newton's laws. Gravity was a cord connecting bodies, the Earth bound to the sun by an invisible string, but Einstein replaced the string with something stranger. He replaced it with curvature. In his universe, planets didn't orbit because they were tugged. They moved the way marbles roll along a warped surface, following the curves of space-time. The Earth was not pulled by the sun. It fell continuously around it, falling forever along the lines. Written into the invisible fabric of the cosmos, it was a revelation both mathematical and metaphysical, because to say that space-time could bend was to say that existence itself could be sculpted. The cosmos was no longer static, no longer a cold mechanical machine. It was alive with geometry, dynamic and breathing. Every object that had mass became an artist, shaping the stage upon which it moved. When Einstein sent his final paper to the Prussian Academy of Sciences, few could understand it. Even among physicists, the language of curved space-time felt incomprehensible. How could emptiness curve? What did it mean for time itself to be distorted? It sounded more like poetry than physics. And yet, deep within the mathematics, there was undeniable truth. The equations predicted things no human had ever imagined. Light bent by gravity, time slowed by motion, and black holes born from collapsing stars. Still, a theory is only as strong as the evidence that supports it. And in 1915, there was none. The proof would come 4 years later, in the spring of 1919, far from Europe's war-torn lands, on the island of Principe off the west coast of Africa. An English astronomer named Arthur Eddington prepared for one of the most delicate experiments in history. His goal was as audacious as Einstein's theory itself: to photograph the bending of starlight around the sun during a total solar eclipse. According to Newton, light should travel in a straight line, but Einstein's equations predicted otherwise. If space-time curved around the sun, then light, though massless, would follow that curvature, deflected as if space itself had tilted. Eddington and his team set up their fragile telescopes beneath the thick tropical air. They waited through the heat, the insects, and the threat of rain. Then, on May 29th, the moon began to slide across the face of the sun. The sky dimmed. The stars of the Hyades cluster emerged faintly near the black disk of the eclipse. And in those brief 6 minutes of darkness, the universe whispered its truth. The starlight did not travel straight. It bent. Exactly as Einstein had said it would. When Eddington returned to England and developed the plates, he found what the equations had promised. Starlight deflected. By spacetime itself, it was the first experimental proof of general relativity. The headlines erupted across the world. Revolution in science. They read, Newtonian ideas overthrown. For the first time in history, the human mind had witnessed the bending of reality. The cosmos was no longer a clockwork of invisible forces. It was a living continuum. Einstein became a global icon overnight. But more importantly, the universe itself changed in the human imagination. The idea of space-time, that the fabric of reality could warp and ripple, reshaped not only physics, but philosophy, art, and the very way humanity saw itself. Space was no longer the emptiness between things. It was a medium, a structure, a kind of cosmic ocean upon which galaxies floated like islands, and time, once thought to flow evenly everywhere, became something elastic. Time could slow in the presence of gravity. It could twist near the speed of light. The ticking of clocks was no longer universal. It was woven into the geometry of the universe itself. This was the true birth of modern cosmology. Because once scientists understood that space and time were flexible, they could begin to imagine a universe that changed, expanded, and evolved. The static heavens of the ancients became an unfinished story, and at the center of that story was the realization that existence was not built. It was woven mathematically. Space-time could be described with 4 coordinates, 3 for space, 1 for time, but physically, it was far more profound. It meant that every event, every particle, every atom, every moment in history existed not as an isolated thing, but as part of a continuous geometry. The fall of an apple and the orbit of a planet were both curves on the same vast sheet of reality. As scientists absorbed this, they began to see new consequences hidden in Einstein's equations. If space-time could bend, it could also collapse. And from that collapse, something extraordinary might emerge. A point where curvature became infinite. A singularity, the seed of what would later be called a black hole. The equations also implied the possibility that the universe itself had a curvature, that it might be expanding or contracting. But in 1915, even Einstein hesitated to believe that he introduced a cosmological constant, a mathematical fix meant to hold the universe steady, to keep it from moving. He could not yet imagine a cosmos in motion. Yet in that hesitation lay the next revolution, one that would unfold decades later, when Edwin Hubble looked into the deep sky and saw galaxies fleeing from one another, confirming that space itself was stretching. Still, none of that was visible yet. In 1919, humanity was simply awakening to a new kind of existence. The idea that reality was geometry, that mass told spacetime how to curve, and spacetime told mass how to move, became the foundation of everything to come. Through this discovery, Einstein had not only rewritten gravity, he had redefined what it meant to be. If space could bend and time could stretch, then the cosmos was not a backdrop at all. It was a participant, a living fabric that could feel the presence of matter, respond to energy, and carry the memory of motion through its folds. Over the following years, physicists and mathematicians worked to test and refine Einstein's vision. From Karl Schwarzschild's exact solution for a point mass, the first mathematical description of a black hole, to Willem de Sitter's empty universe that hinted at cosmic expansion. Each solution revealed a new facet of the same geometry. Spacetime was not merely curved, it was expressive. It contained potential. It could ripple like water, it could trap light, create horizons, and define the limits of what could ever be known To describe the universe was now to describe a landscape of curvature. A vast, dynamic terrain shaped by the silent dialogue between energy and geometry. In the quiet aftermath of the discovery, philosophers began to see echoes of something timeless. If all of existence was geometry, then perhaps geometry was the language of reality itself. Every law, every particle, every field might emerge from the way space-time chose to fold, to study. Physics was to trace the wrinkles of a cosmic fabric, an invisible architecture stretching through all things. Einstein, reflecting years later, said that his greatest joy was not in the fame, but in the simplicity of the idea that gravity was not a pull, but a shape so elegant, so complete, that even light could not escape its influence. He once wrote, "The most incomprehensible thing about the universe is that it is comprehensible." And in that statement lay a quiet wonder, that human thought could reach beyond stars, beyond time, into the silent geometry that sustains everything. From that moment on, the universe would never again be seen as still. It would ripple, stretch, and breathe. The heavens would become fluid, alive with gravitational waves, and every motion, from a falling apple to the orbit of a galaxy, would be seen as the echo of a deeper curvature. Humanity had finally looked beyond matter and seen the architecture itself. They had discovered that reality was not composed of things, but of relations, of curves, of warps, of the silent dialogue between space and time. In that revelation, the old universe, the mechanical one of gears and levers, quietly dissolved, and a new one took its place. A universe not built, but woven. The stars were no longer distant fires scattered through emptiness. They were patterns written into a living geometry, a fabric that bent under their weight and shimmered with their light. This was the moment the cosmos revealed its structure. The moment humankind understood that it did not live in space. It lived within the fabric of space-time itself. And for the first time, it began to listen, not to the pull of gravity, but to the silent curvature of reality. By the 1920s, the world of physics was still glowing in the light of Einstein's revelation. Space and time had been united, gravity had become geometry, and the universe itself was a living fabric. Yet even as this vast new vision settled into the minds of scientists, another revolution had already begun, one that would quietly shatter its certainty. A different kind of discovery, born not in the heavens, but in the heart of the atom. At first, it seemed a small thing, an anomaly in the glow of heated metal. In 1900, Max Planck had been studying the color of light emitted from hot objects, a problem that had defied classical physics. According to Newtonian and electromagnetic theory, the higher the frequency of light, the greater its energy, without limit. But in reality, matter refused to emit infinite energy. Something stopped it, as though the universe itself imposed a secret rhythm. Planck found that light didn't radiate continuously, but in tiny, discrete packets, quanta. Energy, he realized, was not a flowing stream, but a collection of indivisible drops. And with that, a crack opened in the smooth surface of reality. It was a simple equation, but behind it lay a deep philosophical fracture. If energy came in quanta, then the foundations of nature were not continuous. They were grainy, discontinuous, unpredictable. The fabric of existence, which Einstein had imagined as smooth and supple, might instead be woven from jittering, indivisible threads. In the following decades, this strange new world expanded. Physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger began to probe the behavior of atoms and electrons. What they found was nothing short of heretical. Electrons did not move in predictable orbits like planets around a star. They existed in clouds of probability, in superpositions of every possible state until observed. At the smallest scales, certainty itself seemed to dissolve. In 1927, Heisenberg revealed the uncertainty principle, a law that said the more precisely one measured a particle's position, the less precisely one could know its momentum. Reality, at its most fundamental level, refused to reveal itself fully. It was as if the act of measurement itself disturbed the universe, collapsing possibility into a single fleeting truth. The observer could no longer stand apart from the observed. The mirror of nature had cracked, and through those cracks, an ocean of mystery shimmered. Quantum mechanics had arrived, and it spoke in riddles. It described a world where particles were also waves, where existence itself flickered in and out of being. A photon could travel two paths at once. An electron could pass through both slits of an experiment simultaneously, interfering with itself as if it were a ghost. The old idea of a definite objective world was gone. In its place stood a universe woven from uncertainty and chance. For Einstein, this new picture was intolerable. He had spent his life revealing the deep, orderly geometry of space-time, a cosmos of cause and consequence, of elegant curvature and mathematical beauty. But now, his contemporaries were telling him that beneath that beauty lay chaos, that reality itself might be governed not by law, but by luck. God does not play dice with the universe, he once wrote. Unable to accept that the cosmos he had mapped so carefully might be built upon randomness, Bohr disagreed. He believed that uncertainty was not a flaw. It was a feature, a fundamental truth of existence. The quantum world did not need hidden causes. Its chaos was complete, self-contained, and absolute. The two visions could not be reconciled. One described a smooth, curved space-time where every event was connected through geometry. The other revealed a storm of flickering probabilities, where reality did not exist until it was measured. And so, the fabric of understanding began to split. At the human scale, relativity and quantum mechanics each worked perfectly within their own realms. Einstein's equations described planets, stars, and the dance of galaxies with flawless precision. Quantum theory predicted atomic behavior, lasers, and semiconductors with equal accuracy. Yet when scientists tried to unite them, to describe what happened where both gravity and quantum forces mattered, such as inside black holes or at the birth of the universe, the mathematics broke down. The equations exploded into infinities, as if the two worlds refused to coexist. It was as though nature had drawn a veil between the very large and the very small, a boundary between the cosmic and the subatomic. Still, the search continued. Physicists began to explore what space-time itself might look like at the smallest conceivable scale. The Planck length, about 10 to 3510, 35 meters. Here, even the idea of smooth geometry begins to unravel. At such scales, according to John Wheeler, space-time would be anything but calm. It would churn and fluctuate like the surface of a stormy sea. This restless underlayer became known as quantum foam. In this foam, space and time are no longer continuous. Tiny bubbles of space-time appear and vanish within trillionths of a second. Quantum fluctuations warp geometry itself, bending and twisting it at unimaginable speeds. Particles pop into existence and then annihilate, releasing ghostly ripples that never quite fade. The universe, it seems, cannot sit still. Not even in perfect vacuum, even emptiness hums. If Einstein's universe was a calm ocean of space-time curvature, then the quantum universe is a boiling cauldron beneath it, foaming with ephemeral creation. The contrast could not be more extreme. One is continuous, the other discrete. One is deterministic, the other uncertain. And yet, both claim to describe the same universe. This contradiction between the smooth geometry of relativity and the chaotic graininess of quantum mechanics became the great paradox of modern physics. It is not merely a technical puzzle, but a philosophical one. It asks what reality truly is. Is space-time fundamental, as Einstein believed, a real, continuous medium shaping the motion of matter? Or is it an illusion, a statistical blur emerging from something deeper and discrete? The cracks in the fabric widened with every new discovery. When scientists studied particles at high energy, the forces between them began to blur. Electricity and magnetism unified into a single electromagnetic field. The weak nuclear force joined them, but gravity, the eldest force, the shaper of stars, remained apart, stubbornly incompatible with the quantum realm. It refused to fit into the same framework, as though it were speaking a language the others could not understand. This divide gave rise to a haunting realization. Perhaps the universe has two blueprints, one written in the language of curves and the other in the language of quanta. One describes the vast cosmic architecture that binds galaxies and warps light. The other governs the restless dance of particles and fields beneath. Together they build everything, yet they refuse to meet. To scientists, it was as if the cosmos itself were guarding a secret a hidden layer beneath spacetime where both worlds might merge. The deeper they looked, the more elusive it became. Every experiment confirmed the accuracy of both theories within their domains, and every attempt to unite them ended in contradiction. It was not just a mathematical problem, it was a metaphysical fracture at the core of reality. In the decades that followed, the tension only deepened. Einstein, in his final years, worked tirelessly to find a unified field theory, one that would merge gravity and electromagnetism into a single elegant framework. But the equations refused him. He died with his notes unfinished, his chalk still stained with the search for a deeper geometry. He had spent his life describing the smooth curves of the cosmic stage. But beneath that stage, the quantum storm continued to rage. Meanwhile, younger physicists ventured further into the uncertainty he had resisted. They discovered that quantum theory was not only correct, it was essential. It predicted the structure of atoms, the stability of matter, the birth of stars, even the radiation from black holes. Einstein's world and the quantum world could not be dismissed. They were both true, and yet together, they were impossible. Thus began the modern quest for what physicists now call quantum gravity, the effort to describe space-time itself as a quantum phenomenon. The search for a theory that could heal the fracture, uniting the continuous with the discrete, the smooth with the chaotic. Some believe space-time may not exist independently at all, that it might emerge from entanglement, from information, from invisible symmetries yet to be discovered. Others imagine that it is composed of fundamental atoms of space, microscopic loops or strings vibrating at the edge of comprehension. Whatever the answer, the question remains the same. If space-time can bend, ripple, and collapse, what is it made of? What lies beneath the smooth illusion of continuity? The deeper scientists look, the more the universe seems to hint at hidden builders, the silent architects whose work underlies both geometry and chaos. The cracks in the fabric are not flaws. They are glimpses of something beneath, something that stitches the two realms together, the cosmic and the quantum, the wave and the curve, the smooth and the shattered, coexisting in impossible harmony. And in that tension, the modern story of physics begins. The search for the architecture beneath space-time itself, the search for the invisible hands that weave both order and uncertainty into the same vast design. There was a time when physicists imagined space as a perfect emptiness, a quiet background stretching endlessly between the stars. But as instruments grew sharper and equations more daring, that silence began to dissolve. Beneath the apparent stillness of the void, something alive was stirring, restless, invisible, and infinitely intricate. In the mid-20th century, as the dust of quantum revolution settled, scientists turned their gaze inward, into the infinitesimal depths of reality. What they found defied all notions of emptiness. Space, they discovered, was not hollow. It was alive with activity, trembling with unseen energy. The closer they looked, the more space itself seemed to shiver. This was the birth of quantum field theory, a new language of nature where particles were no longer tiny, isolated specks of matter, but excitations, ripples, brief songs within vast invisible seas. Every kind of particle corresponded to its own field. Electron fields, quark fields, photon fields, infinite invisible fabrics, woven through every corner of existence. The universe, in this view, was no longer built from particles at all. It was a symphony of vibrations, each note giving rise to what we call matter, energy, and even light itself. The void was no void. It seethed with fleeting forms, pairs of particles emerging from nothingness, then vanishing back into it in less than a trillionth of a second. They appeared not from nowhere, but from the restless energy of the quantum vacuum, a background hum that never ceased, a kind of cosmic breathing beneath reality's skin. In 1948, the physicist Hendrik Casimir proposed an experiment that would give this ghostly energy a tangible presence. When two metal plates were placed extremely close together, he predicted, the quantum fluctuations between them would differ from those outside. The imbalance, subtle but real, would generate a measurable force, as if the void itself were pressing the plates together. Years later, the effect was observed. The vacuum, it turned out, could push. The nothingness had weight. Physicists began to suspect that this invisible ocean of energy was not only real, but fundamental. Every atom, every spark of radiation, every gravitational wave might be a visible crest on this invisible tide. Then, another discovery deepened the mystery. In the 1960s, theoretical physicists Peter Higgs, François Englert, and others proposed that there exists a pervasive field throughout the universe. One that interacts with particles to give them mass. Without it, everything would move at the speed of light, unable to clump, unable to form atoms, stars, or life. It was called the Higgs field. To understand its role is to imagine an invisible fog filling all of space. As particles pass through it, some are slowed, acquiring mass. Others slip through nearly untouched, remaining light and fast. What we perceive as weight, inertia, and the solidity of matter is, in truth, the gentle drag of an unseen medium that underlies reality. For decades, the Higgs field remained an elegant theory, its existence unconfirmed. Then, in 2012, deep beneath the Swiss-French border, at the Large Hadron Collider, scientists finally glimpsed its echo. The Higgs boson, the particle manifestation of the field itself. It was the faint shimmer of a field that had been there all along, silently shaping everything that exists. With that discovery, the idea of the universe as a vacuum, an empty arena, finally collapsed. What we once thought of as space was, in truth, a dense fabric of fields, humming with quantum energy and vibrating with invisible tension. And so emerged a new picture of existence, one both exhilarating and unsettling. The geometry of spacetime, as Einstein had revealed, describes the large-scale shape of reality. But these quantum fields suggested something deeper. Perhaps spacetime itself was not the foundation. Perhaps it was a phenomenon that emerged from these invisible energies, a byproduct of something even more fundamental. To imagine this is to invert everything once believed. Instead of particles moving through space, space itself may arise from the collective relationships of the fields. The lattice of space-time could be the shadow of something that hums beneath, a silent architecture, unseen but omnipresent. Physicists such as John Wheeler and Richard Feynman wrestled with this paradox. Wheeler imagined the fabric of space not as continuous, but as a quantum foam, a bubbling chaos of fluctuations at unimaginably small scales. The Planck length, a trillion times smaller than an atom. Here, the smooth curves of Einstein's geometry dissolve into frothing unpredictability. Everywhere, space-time itself may flicker, bend and knot, forming transient wormholes and loops that appear and vanish too quickly to measure. Beneath the calm surface of reality, the universe could be forever churning, its foundations constantly rewritten by invisible motion. Even the vacuum's energy, the sum of all these microscopic jitters, defies comprehension. Quantum theory predicts it should be enormous, enough to tear the universe apart, and yet cosmological observation suggests it is astonishingly small. This mismatch, the so-called vacuum catastrophe, is one of the greatest unresolved puzzles in modern physics. Something, somewhere, seems to be balancing these forces with exquisite precision, as if the cosmos were tuned by invisible hands. The more scientists measured, the more mysterious the void became. At its heart lies vacuum energy, the most paradoxical concept in all of science. It cannot be seen, yet it shapes the motion of galaxies. It cannot be isolated, yet it defines the fabric of spacetime. It whispers in the form of the cosmological constant, a term Einstein once introduced, then abandoned, and which later returned as a clue to the universe's accelerating expansion. Some theorists now wonder, could the same hidden fields that ripple beneath quantum scales also be responsible for the cosmic push that drives galaxies apart? Could the energy of nothing be the engine of everything? If so, then the structure of reality may not rest upon atoms or stars, but upon tension, a delicate balance between presence and absence, between energy and the void that contains it. Every point in the cosmos, every moment in time, may be woven from this invisible strain. The Higgs field, the electromagnetic field, the gluon fields that bind quarks inside protons, all may be threads of a deeper tapestry that we have not yet seen in full. What we call matter could be the music of those threads, their vibration frozen into form. The more physicists probe this hidden realm, the more they encounter an uneasy beauty. Space is not an emptiness between things. It is a thing itself. The void breathes, fluctuates, creates and destroys without pause. The silence between the stars is a silence filled with motion. And yet, there is a haunting implication behind all this. If fields are the true substance of existence, then everything tangible, from mountains to mines, is an illusion of stability, a pattern written on something that never rests. To understand the fields is to glimpse the invisible tension that sustains the universe. It is to sense the quiet hum that fills even the darkest reaches of the cosmos. From this hum, perhaps space-time itself arises, a geometry sculpted not by force, but by resonance. And in this resonance, one can almost hear the faint breath of the silent architects. Those unseen laws, those hidden symmetries, those mathematical whispers that give rise to all that is and all that will be. It is here, in this unseen tension beneath everything, that the universe hides its most profound secret, that existence is not built from matter, nor from space, nor from time, but from the endless vibration of what cannot be seen, a silence that is never truly silent, a void that is never truly empty, a foundation that hums beneath all foundations. Gravity has always been the quietest of the forces and the most mysterious. It binds galaxies, sculpts stars, and steadies planets into their paths. Yet it whispers rather than shouts. Among the four fundamental forces of nature, it is the weakest by far, weaker than electromagnetism, weaker than the nuclear forces that hold atoms together. And yet, on the grandest scales, it dominates everything. It governs the architecture of the universe itself. When Albert Einstein completed his general theory of relativity in 1915, he redefined gravity not as a force, but as the bending of space-time itself, a consequence of mass and energy curving the geometry of existence. Planets move not because they are pulled, but because they follow the contours of a cosmic landscape, distorted by the presence of matter. It was a revelation that changed everything. But Einstein's insight carried an eerie implication. If space and time can bend, then surely they can also vibrate. In 1916, Einstein predicted that violent events in the cosmos, colliding stars, exploding supernovae, the birth of black holes, would send ripples through the fabric of space-time, waves traveling at the speed of light. These would not move through space, but would be oscillations of space itself. He called them gravitational waves. For a century, they remained a ghost in the equations, too faint, too elusive to capture. Space trembled, but the instruments of the 20th century were deaf to its whisper. Then, 100 years later, in a quiet observatory on Earth, the universe was heard for the first time. It was September 14, 2015. Deep beneath the American countryside, two enormous detectors known as LIGO, the Laser Interferometer Gravitational Wave Observatory, listened to the silence. Twin beams of light, each 4 kilometers long, bounced between mirrors so precise they could detect a distortion smaller than a fraction of a proton's width. For months, the instruments waited. And then, the signal arrived. A faint chirp, lasting less than a second, rippled through the data. It was the echo of two black holes colliding over 1 billion light-years away. In that moment, space-time itself had spoken. The waves that reached Earth had begun their journey long before life crawled from the seas. They had stretched and squeezed the universe as they traveled, carrying the memory of an unimaginable violence. Two suns, each 30 times the mass of our own, spiraling toward one another, merging into a single black hole. For the first time in history, humanity had not seen the universe. It had heard it. The sound of the cosmos was not the crackle of static or the hum of stars, but a low, rising note, the final heartbeat of a dying orbit. Einstein's century-old prediction had come alive, and with it, a new sense of awe. These waves are distortions not of matter, but of reality itself. They stretch time. They compress space. When they pass through Earth, every atom, every person, every mountain, and every ocean expands and contracts, imperceptibly, yet profoundly. What LIGO detected was not a vibration in the universe. It was the vibration of the universe. It is difficult to imagine such a thing. A ripple in space-time means that the distances between stars, between atoms, are not fixed, but fluid. Geometry itself becomes a trembling medium, like water responding to an unseen tide. The universe, once thought silent, is in constant motion, humming in frequencies too deep for human senses. Yet even as physicists learned to listen, the mystery of gravity only deepened. Among all the forces, gravity remains the only one that resists a quantum description. Electromagnetism, the strong and weak nuclear forces. Each has been successfully woven into the quantum framework, described by exchange particles and field equations that predict their every behavior. But gravity refuses. Attempts to quantize it, to find the so-called graviton, the hypothetical quantum of gravitational force, have so far failed. The mathematics breaks down, infinities appear, and the theory collapses into paradox. Einstein's smooth geometric spacetime and the jittering chaos of quantum mechanics seem to speak incompatible languages. One describes the grand curves of the cosmos, the other, the jittering foam beneath. Between them lies a fracture, the deepest rift in modern physics. Gravity, the architect of galaxies, remains an outsider in the quantum world. And so, a question lingers. If spacetime can tremble, can it be made of something? When a guitar string vibrates, it does so because it is stretched, held in tension. What then is the string of spacetime stretched across? What lies beneath the waves? Some theorists believe that gravity might not be fundamental at all. Instead, it could be emergent, a shadow cast by something deeper, something built from microscopic degrees of freedom that we cannot yet see. Just as temperature arises from the motion of unseen molecules, gravity might arise from the collective behavior of hidden entities, bits of information woven into the very structure of space. This idea has many faces, from the holographic principle to emergent gravity models, but each carries a haunting implication. Space-time might not be the stage of the universe, but a construct that emerges from a deeper, invisible order. When the black holes merged, they did not simply create waves in emptiness. They may have disturbed that deeper order itself, shaking the unseen architecture that gives rise to geometry. In 2017, LIGO and its European counterpart, Virgo, detected another gravitational wave, this time from the collision of two neutron stars. Unlike black holes, neutron stars are made of matter, so their collision released not only gravitational ripples, but a burst of light, gamma rays, and heavy elements. For the first time, humanity saw and heard the same event in two languages, gravitational and electromagnetic. This was the birth of multi-messenger astronomy, a way of listening to the universe with new senses. And yet, even this triumph hinted at deeper puzzles. The signals matched Einstein's equations perfectly, but beneath that precision lay silence. Silence about what space-time truly is. If the universe can shake, what is doing the shaking? Some physicists propose that space-time may behave like a quantum medium, perhaps composed of Planck-scale structures, unimaginably tiny units of area and volume, woven into a network that defines distance and duration. In this picture, gravitational waves are like ripples across that microscopic lattice, the universe vibrating at its most fundamental level. Others imagine a more exotic picture, that gravity arises from entanglement, the invisible links between quantum particles. When these connections shift, space itself may curve. Geometry could be nothing more than the shadow of quantum information organizing itself. These are speculations, fragile bridges between two incompatible worlds, yet they point toward an unsettling truth, that gravity, for all its familiarity, may be the least understood aspect of existence. Its presence defines our reality, yet its nature defies comprehension. It is at once infinite and weak, geometric and dynamic, smooth and trembling. It shapes the fate of stars, the flow of time, the expansion of the cosmos. And still, no one truly knows what it is. To feel gravity is to be connected to everything. To study it is to confront the structure of being itself. When gravitational waves pass through the Earth, they leave no mark, no sound, no heat, only a whisper in the mathematics, a distortion in the light of lasers deep underground. Yet in that whisper lies the story of creation and destruction, of cosmic collisions beyond imagination. A pair of black holes colliding halfway across the universe can make the very fabric of existence tremble here. In the stillness of human observation, the entire cosmos, across unimaginable distances, behaves as one continuous whole. And so, scientists listen to the faint murmurs of distant cataclysms, to the echoes of the early universe, to the silent language of space-time. Each detection is a message from the depths of reality, revealing not what we see, but what we are. The silence of space is not empty. It is woven with tension. Every tremor, every vibration is a reminder that geometry itself can move, can sing, can feel. The universe is not a still painting. It is a living fabric, stretching, bending, trembling, and within those tremors may lie the first hints of what the universe is made from, and of the silent architects who shaped it. Because if space-time can quiver like a string, then perhaps it has strings indeed, invisible, fundamental, and ancient, vibrating at the edge of perception, composing a song that is older than time. And perhaps in that song, we may one day hear the true voice of gravity, not as a force, but as the trembling of reality itself. At the edge of understanding, where the light of distant galaxies fades into red and silence, the universe hides its greatest secret. For centuries, astronomers believed the cosmos was slowing down, that gravity, the invisible glue of all things, was pulling on the galaxies, gradually halting their outward rush since the Big Bang. It seemed inevitable that expansion would one day stop, and the universe would begin to fall back upon itself, collapsing into darkness. But the universe had other plans. In 1998, two teams of scientists studying distant supernovae, the Supernova Cosmology Project and the High-Z Supernova Search Team, uncovered something that shattered everything known about cosmic destiny. They were measuring the brightness of Type Ia supernovae, stellar explosions that serve as cosmic mile markers, each one burning with a predictable light. By comparing how dim these explosions appeared, they could calculate how far away they were, and how fast the universe had expanded since their light began its journey. What they found was impossible. The supernovae were dimmer than expected, not because they were farther back in time, but because the universe had sped up since their light was born. The expansion of the cosmos was not slowing, it was accelerating. Space itself was stretching faster and faster, as though some invisible hand were pulling the galaxies apart. In that instant, everything humanity thought it knew about the cosmos turned inside out. This mysterious force, unseen yet immeasurable in power, was given a name that offered no comfort: dark energy. It was a name born of ignorance, not understanding, a placeholder for the unknown. But the implications were staggering. If dark energy truly existed, it must make up the overwhelming majority of the cosmos. Astronomers began to take stock of the universe's contents, and the reckoning was humbling. Everything familiar, stars, planets, nebulae, and all the galaxies visible across the heavens, amounted to less than 5% of reality. The rest, 95%, was composed of things no telescope could ever see. Roughly a quarter was dark matter, the unseen scaffolding that holds galaxies together. The remaining 70%, the vast majority of existence, was this mysterious dark energy, a force without particles, a pressure without source. The cosmos, it seemed, was built from what cannot be seen. Einstein had once included a term in his equations of general relativity called the cosmological constant, a mathematical trick to hold the universe in static balance. He introduced it reluctantly, later calling it his greatest blunder. Yet, decades after his death, the idea returned. No longer as an error, but as a possible key. The cosmological constant could describe a property of space-time itself, a built-in energy of the vacuum, a gentle repulsive pressure pushing everything apart. If this were true, then the expansion of the universe was not being driven by some external force, but by space itself, the very fabric of reality, stretching from within. Dark energy, in this interpretation, is not a wind blowing through the cosmos. It is the fabric's own breath. The deeper scientists looked, the stranger it became. Measurements of the cosmic microwave background, taken by satellites such as WMAP and later Planck, confirmed the acceleration. The universe's geometry appeared nearly flat, and yet its fate was being dictated by something unseen. The vacuum, once considered empty, now seemed to be alive again, filled with potential energy that refused to vanish. Quantum field theory, the same framework that revealed virtual particles and the restless hum of the vacuum, predicted that even nothing has energy. Every point in space, every cubic centimeter of emptiness, seethes with activity. If one could somehow extract this energy, even a teaspoon of space could hold more power than all the stars combined. Yet there was a problem, one so immense it was almost absurd. The vacuum energy predicted by quantum theory was 120 orders of magnitude greater than what astronomers observed. It is the largest discrepancy between theory and measurement in all of science, a failure so profound it suggests something fundamental is missing. Perhaps some whisper. Dark energy is not the vacuum's natural pressure. Perhaps it is a new field entirely, a cosmic presence woven invisibly into the geometry of space-time. Physicists have given this idea many names: quintessence, phantom energy, scalar fields, but all attempt to answer the same question. Why is the universe accelerating? And what exactly is doing the pushing? If it is a field, then it might evolve with time, changing its strength, shaping the universe's destiny in ways not yet understood. It might decay, it might fade, or it might grow stronger, leading to a distant future where galaxies are torn apart, atoms unravel, and the very concept of distance ceases to have meaning. For now, no one knows. What is certain is that the expansion of the universe is not slowing. It is increasing. Every second, every heartbeat, the fabric of space stretches a little more, and the galaxies drift farther into darkness. The light that leaves them today will never reach us. They are sailing beyond the horizon of visibility, into a realm of cosmic solitude. If this trend continues, one day in the far future, only a few galaxies will remain visible, the local group bound by gravity. To any distant observer, the universe will appear static, cold, and lifeless once again. The cosmic story will fade into silence, its origin forgotten, its architects unseen. Dark energy, then, is both the maker and the unmaker, the quiet engineer of cosmic isolation. But perhaps there is another way to see it. Perhaps the universe is not being pushed apart at all. Perhaps it is growing from within. Like a living organism, space could be expanding not because of some external explosion, but because of an intrinsic property of its own nature, an unfolding, a self-creation. Every moment, the vacuum might be giving birth to new space, new time, new reality, drawn from an energy we do not yet understand. In this view, the cosmos is not racing outward, it is blossoming. Its acceleration is not destruction, but growth. Einstein's equations already hint at such a possibility. If energy is embedded within space-time, then expansion may simply be the universe expressing itself, geometry responding to its own hidden tension. The galaxies do not flee one another. The space between them becomes more of itself. It is a poetic paradox. The universe expands into nothing, yet nothing itself is the source of expansion. To peer into the night sky is to see this silent process at work. Galaxies drifting away not through motion, but through the creation of new distance between them. The cosmos is not moving through something. It is the something that moves. Dark energy, in this sense, may be the universe's own breath, slow, vast, and ceaseless. And so, scientists continue their search. They build telescopes that can measure the dimmest galaxies, the faintest distortions in starlight, the smallest changes in cosmic expansion. Missions like Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed to probe the invisible pressure shaping all of existence. Each seeks to understand what dark energy truly is: a property of space, a quantum field, or something even stranger that transcends both, But beyond equations and data lies a deeper reflection. If 95% of the universe is invisible, then perhaps visibility was never the true measure of reality. Perhaps what we call matter is merely a ripple, a brief flicker in a sea of unseen energy that defines all that exists. The galaxies, their stars, their dust and light, may be nothing more than traces upon an unseen ocean, shadows cast by an underlying presence that has no form, no color, no boundary. In this way, dark energy becomes more than a mystery of physics. It becomes a whisper of philosophy. The universe does not expand outward in violence. It unfolds from within, guided by silent architects that neither shine nor decay, but simply are. A universe built not from matter, but from tension. Not from explosion, but from emergence. Not from chaos, but from geometry learning to breathe. And in the vastness of that breath, across billions of years, across the cold gulf of expanding silence, everything that has ever been, and everything that will ever be, drifts on a current we cannot see. Dark energy may not be an external force. It may be the heartbeat of space-time itself, an invisible rhythm shaping the song of creation, one pulse at a time. In the silence, after Einstein's equations had settled into the foundations of physics, a new whisper began to rise, a question too deep to ignore. What is space-time made of? For decades, physicists had treated it as smooth, continuous, almost divine in its simplicity, but at the smaller scales, the illusion began to falter. The equations of general relativity, so graceful in describing the grand arcs of galaxies, collapsed into chaos when turned toward the subatomic, the quantum world. Restless and uncertain, refused to fit into the serene geometry of Einstein's cosmos. Something deeper must connect the two, something that binds gravity to the quantum sea beneath. Thus began one of the most audacious quests in human thought, the search for quantum gravity, a search for the invisible lattice that holds the universe together. In the late 20th century, a new vision took shape. String theory. It began with a strange idea, that the fundamental building blocks of the universe were not particles, but vibrating strings of energy, each string impossibly small, a trillion times smaller than an atom, trembled in dimensions beyond ordinary perception. Its frequency determined what it became. A low vibration, an electron, a different mode, a photon, a special elusive tone, the graviton, the hypothetical carrier of gravity. In this vision, everything, matter, force, even space-time itself, arose from the dance of strings across an unseen symphony. The cosmos became music, the laws of physics, its score to make sense of these vibrations. The theory demanded more dimensions, 10 or perhaps 11, curled upon themselves in hidden geometries too small to see. The mathematics was beautiful, but also mercilessly complex. For every equation that explained one mystery, a dozen new ones appeared. Still, the idea persisted because in its rhythm, string theory offered something no other framework had, a glimpse of unity. If the fabric of reality were woven from vibrating strings, then gravity was not separate. It was simply another note in the cosmic melody. Yet, not all physicists were convinced. Some turned away from the dream of hidden strings and focused instead on geometry itself. What if space-time wasn't smooth at all? Loop quantum gravity proposed a different kind of structure. It suggested that space is made not of points, but of loops, tiny quantized rings of energy that interlock like a vast, shimmering web. At the smallest conceivable scale, the Planck length, the universe might resemble a woven network. Each intersection of loops, called a node, holds a finite chunk of volume. Each link between them, a thread of area. Together, they form a discrete, granular fabric, no longer continuous. But digital a lattice of space itself in this theory, geometry becomes a quantum entity. The smoothness of space-time is only an illusion that emerges when we zoom out. Much like how a painting seems fluid from afar, but is, up close, nothing but countless dots of pigment, if string theory sang of harmony. Loop quantum gravity spoke of architecture. Both sought the same revelation, the hidden order behind the curtain of existence. As these visions grew, another idea quietly took root: that information, not matter, might be the ultimate foundation of the universe. It was a concept born from the physics of black holes in the 1970s. Stephen Hawking and Jacob Bekenstein discovered that black holes possess entropy, a measure of information. This meant that a black hole was not merely a void, but a kind of cosmic storage device. Its surface, the event horizon, encoded the information of everything it had swallowed. This paradox led to an astonishing hypothesis. Perhaps the universe itself is a kind of hologram according to the holographic principle. The three-dimensional world we inhabit could be a projection from information stored on a distant, two-dimensional boundary. Every particle, every galaxy, every moment, encoded, like light through a holographic plate. Space and time themselves might be emergent, shadows cast by something deeper and more abstract, if true. The universe is not built of matter or even fields. It is built of information, pure relationships, patterns of energy, exchanging messages at the smallest possible scale. Reality, in this view, is not a thing. It is a computation unfolding across the void as theories multiplied. A new generation of physicists began weaving them together into something even more profound. They imagined space-time as a network of entanglement, a vast quantum web where each point is linked to every other by invisible threads in this network. Distance is not defined by meters, but by connection. Two particles separated by billions of light years might still share a hidden link through quantum entanglement, their states bound together in a single equation. Recent research suggests that the very geometry of space-time, the shape of the universe itself, might arise from this web of entangled information. In 2017, studies using the holographic model revealed that as quantum entanglement increases, space-time becomes smoother. When it breaks down, geometry itself begins to tear. It is as if space is nothing but the shadow of relationships, a tapestry woven from the unseen harmony of quantum connections. Visuals unfold, the universe as a lattice of glowing nodes, filaments branching out in a grand fractal of light. Each pulse of energy, a calculation, each ripple, a transmission of information. Across this infinite web, galaxies drift like sparks in an immense computation. A simulation, perhaps, but one without a programmer. In this model, everything computes itself. The cosmos is a self-writing code, a recursive story where each particle knows how to be what it is, because the whole network agrees that it must. From this collective agreement emerges the illusion of continuity, the feeling of reality itself. But deep questions remain. If space-time is emergent, what gives rise to the web beneath it? If information is fundamental, who or what processes it? Is the universe truly mechanical, or does it possess some deeper kind of awareness? A self-consistency so perfect it feels alive. Some physicists now describe reality as an information processor, where physical law is the syntax and matter the meaning. In this view, gravity becomes a manifestation of information flow. Space curves not because of mass, but because of entropy gradients, differences in information density across the quantum field. Eric Verlinder's entropic gravity theory proposes exactly this: that gravity is not a fundamental force, but an emergent effect of information trying to balance itself. If so, then even Einstein's fabric might be only a statistical mirage, a macroscopic echo of countless microscopic exchanges between the invisible bits of reality in laboratories and equations. The quest continues. Physicists build ever more sensitive detectors to search for the quantum grain of space-time, the faint whisper of Planck-scale discreteness. Experiments like LIGO and the Event Horizon Telescope hint that subtle patterns in gravitational waves or black hole images could someday reveal the imprint of quantum geometry on the mathematical frontier. Simulations of loop networks and string vibrations attempt to uncover how the continuous emerges from the discrete. And in the space between theory and philosophy, a new paradigm quietly forms: that the universe is not made of things, but made of making process, not product relation, not object. The lattice of everything remains unseen, but its echoes shimmer in every equation, every discovery, every unanswered question. It hums beneath atoms and galaxies alike. It links Einstein's smooth continuum to Planck's restless sea. It may even link mind to matter, as information loops back upon itself, dreaming of form and pattern and consciousness. The search for quantum gravity is not just a scientific pursuit, it is the attempt to read the code of existence itself, the language that writes stars and thought with the same hand. The universe may not be built at all, it may be woven, and in its infinite tapestry, the threads are not material but logical, lines of interaction, loops of cause and consequence. If space-time is indeed a story, then quantum gravity is the grammar that holds it together, and the lattice, silent, unseen, yet everywhere, may be the truest face of the cosmos or universe, not of matter, nor of emptiness but of meaning, endlessly computed into being. In the quiet corridors of theoretical physics, an unsettling idea began to flicker into view, one that seemed to blur the very boundary between what is real and what is illusion. It began not with stars, but with silence, not in the vast stretches of galaxies, but in the shadow of a single, impossible object. The black hole. Black holes were meant to be the universe's most final punctuation marks, regions so dense that nothing, not even light, could escape their gravity. To fall into one was to vanish from history itself, erased from the cosmic record. But in the 1970s, Stephen Hawking uncovered a paradox so profound that it shook the foundation of physics' black holes. He realized, we're not perfectly black through subtle quantum effects near the event horizon. They radiated. And if they radiated, they would slowly evaporate, eventually disappearing. That was the contradiction. If a black hole could vanish, what happened to the information about everything it had swallowed? According to the laws of quantum mechanics, information can never be destroyed, but according to general relativity, it had nowhere to go. Two of the greatest theories in science, the smooth geometry of Einstein and the chaotic precision of the quantum world, stood in irreconcilable conflict somewhere between the curvature of space-time and the shimmer of probability. Reality itself seemed to break in the 1990s. A Dutch physicist named Gerard 't Hooft proposed an idea that would change everything. He suggested that the information of everything inside a region of space could be fully described by the data encoded on its boundary. Every atom, every photon, every event, all of it could, in principle, be written on a surface enclosing that space soon after. Leonard Susskind expanded this vision and gave it a name, the holographic principle. Just as a hologram projects a three-dimensional image from a two-dimensional pattern, the universe itself might be doing the same. Reality, it seemed, could be a projection. The paradox of black holes now found an unexpected resolution. Perhaps the information that seemed to vanish inside was never truly lost. Perhaps it remained imprinted on the horizon, the two-dimensional surface that marks the edge of no return. The event horizon, once thought to be a border of annihilation, became a library. Every particle that fell in left behind a trace, a subtle quantum code written in the fabric of space-time itself. The black hole, far from being a destroyer, was a keeper of records, an archive of everything that had ever crossed its threshold. This idea carried a deeper implication, one that reached far beyond black holes. If information on the surface could describe everything within, then perhaps the entire universe worked the same way. Perhaps the cosmos we inhabit, with its depth, motion, and time, is merely the projection of information stored on a distant boundary. A boundary we cannot see, a horizon so vast it might encompass all of existence in this picture. Space itself becomes secondary. The true reality lies on the edges, where the information is written. We, and everything we perceive as solid or near, might be shadows cast by the slow computation of a higher dimensional surface. It was a theory that defied intuition, but found unexpected support in mathematics. In 1997, Argentine physicist Juan Maldacena offered the first concrete realization of this principle through what became known as the ADS-CFT correspondence. He showed that a universe with gravity, existing in a curved, higher dimensional space, could be equivalent to a universe without gravity existing on its boundary. Two different realities, two languages describing the same thing: gravity, space-time, and geometry on one side, quantum fields, and pure information on the other. A perfect duality. The equations matched, the numbers sang in harmony. Suddenly, what had seemed like metaphysical speculation began to feel like revelation. The holographic principle was not just a poetic metaphor, it was a mathematical truth. If this idea is real, then the world around us is both true and not true. The table beneath a hand, the air that moves through lungs, the light that travels from stars. All might be emergent phenomena patterns, not particles projections. Not building blocks, reality becomes a kind of mirage, one that doesn't vanish upon approach, but deepens the closer it is examined. At its heart lies a quiet, haunting symmetry. What we call the interior of reality may not exist independently of its boundary. Every vibration of space-time, every quark and gluon could be the echo of data on a cosmic screen. The universe may not be expanding into emptiness at all. It might be unfolding from information encoded long ago on a horizon that still surrounds us. To visualize this is to stand on the edge of comprehension. Imagine the cosmos as a vast, translucent sphere on its outer shell. Patterns of quantum information shimmer and shift. From this layer, this boundary, the three-dimensional universe within is generated. Every star, every atom, every mind, projections formed from the endless computation of that surface. The silent architects that have haunted this story now take on new form. They are not beings, nor forces, they are relations. Bits of information entangled in perfect symmetry, whispers of light and entropy that together create the illusion of depth. In this vision, existence is the harmony of two realities, one that is written and one that is read. But what does it mean for something to be real in such a universe? If space-time, matter and energy are emergent, does their impermanence make them illusion? Or does their coherence, the persistence of law, the consistency of experience, give them a higher kind of truth? Physicists now wrestle with this question, not as philosophers, but as experimentalists. Could the holographic nature of space-time be detected? Could we, in principle, find the grain of the code that writes reality? Experiments such as the Fermilab holometer have sought to detect the faintest vibrations in space itself, fluctuations that might reveal whether the universe has an informational resolution limit. Like pixels in a screen, the smallest measurable units of space-time might betray the presence of the holographic substrate beneath. So far, the results remain inconclusive. The universe keeps its secret. Still, the mathematics continues to evolve. The holographic principle has found echoes in quantum gravity, in string theory, even in the physics of entanglement. In 2013, researchers showed that space-time connectivity itself, the way space holds together, can arise from patterns of quantum entanglement. If the entanglement between two regions of space is broken, their geometric connection dissolves in this light. Space-time is not a fixed arena. It is a network of relationships. An emergent geometry, born from the invisible choreography of information. The holographic mirage, then, is not deception, it is structure. It is order rising from entropy, meaning arising from code philosophically. It is a revelation that humbles and uplifts in equal measure, because it suggests that reality, at its core, is not passive, it is active, self-organizing, self-expressing. The cosmos may not be a thing to be seen. It may be a process that sees itself in the holographic model. Every piece of information is connected to every other. Every pattern participates in the whole, and through this infinite web of mutual definition, the universe knows how to exist. Perhaps this is what consciousness mirrors. The holographic awareness of being each human mind, each act of perception, an echo of the universe observing itself through its own projection. As this understanding deepens, the line between science and metaphysics begins to blur, not through mysticism, but through the profound unity of mathematics and meaning. Einstein's geometry, Planck's quanta, Hawking's paradox, all converge in this vision of a universe that both is and is written. Reality becomes a language, and physics its grammar. The cosmos, a narrative unfolding on the canvas of entropy and light. What began as a paradox in the darkness of a black hole now stands as the key to understanding existence itself. Perhaps the universe is not a thing, expanding outward. Perhaps it is information unfolding inward. The silent architects remain unseen, but their voices are everywhere. In the hum of radiation, in the spin of particles, in the delicate symmetry of the laws that bind the infinite. They are the patterns that make pattern possible, the whispers that turn nothing into something. The authors of reality's mirage, and in their silence, the universe writes itself, one shimmering line of code at a time. In the vast ocean of equations and theories, there is a quiet longing that drives the human mind. The search for simplicity amid the storm of complexity that the universe presents. Physicists sense something beneath it all, a hidden order, a perfect symmetry that once was, and perhaps still is. They call it the cosmic blueprint from the earliest days of science. Every breakthrough has pulled a thread. From the same tapestry, Newton saw the same force that made an apple fall, guiding the moon around the Earth. Maxwell revealed that light itself was the marriage of electricity and magnetism. Einstein took gravity and turned it into geometry. Each discovery did not add more, it subtracted. It made reality simpler behind every apparent chaos. The universe seemed to whisper the same truth. All this complexity was born from something simple in 1915. A German mathematician named Emmy Noether revealed a principle that changed the way physicists understood the world. It was a theorem so profound that every symmetry in nature, every hidden order, implied a law of conservation. The symmetry of time gave rise to energy. The symmetry of space gave rise to momentum. The symmetry of rotation gave rise to angular momentum in one stroke. She revealed that the harmony of mathematics and the permanence of reality were the same thing, that what does not change, what remains conserved, is the echo of a deeper balance. Noether's theorem became a cornerstone of modern physics. It taught scientists that beauty in mathematics was not aesthetic, indulgence. It was evidence where symmetry existed. So did truth, and so the search for symmetry became the search for reality itself. But as scientists peered deeper into the microcosm, they found that symmetry, like light, could be deceptive in the aftermath of the Big Bang. The universe is believed to have been perfectly balanced, a pure and uniform energy field, symmetric in every direction, but as it cooled, something extraordinary happened. The perfect symmetry broke, fields split, forces separated, and particles were born. Gravity drifted apart from the other forces. Electromagnetism diverged from the weak and strong nuclear bonds. Mass appeared. Space expanded, and time began its relentless march out of that fracture, that tiny imperfection in an otherwise perfect state. Everything emerged in physics. This is known as spontaneous symmetry breaking, the process by which the universe, once perfectly balanced, chose a direction, a preference, and from that choice, reality unfolded what appears chaotic today. Galaxies swirling, matter clumping, stars exploding, might be the surface turbulence of a deeper, mathematical order, a whisper of the symmetry that was lost to physicists. This realization carries both beauty and sorrow. Beauty, because it means that every particle, every force, every corner of the universe is a reflection of an ancient perfection. Sorrow, because that perfection no longer exists. It had to break in order to be seen. The universe, in this view, is not an accident. It is the necessary consequence of imbalance. Matter exists because symmetry failed. Structure arises because perfection could not hold. And so, from silence came sound. From stillness, motion. From simplicity, chaos across laboratories and observatories. The hunt for ultimate simplicity continues. Physicists search for a single equation, a theory of everything, that could unify the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. If found, it would reveal the original symmetry that existed before the cosmos shattered into complexity. String theory proposes that these forces are but vibrations of one fundamental object, one equation singing many notes. Loop quantum gravity suggests that space itself is built from tiny loops, woven in self-similar harmony. Others seek the truth in the holographic principle, where reality emerges not from matter, but from information. Each path leads toward the same horizon. The hope that behind the infinite diversity of existence lies a single principle, a simple law. a symmetry unbroken. But nature guards this truth with layers of paradox. Symmetry gives rise to order, yet without its breaking, there can be no form, no stars, no life. The Higgs field, for instance, discovered through the Large Hadron Collider in 2012, is the child of broken symmetry. It gives mass to particles precisely because the universe's original uniformity fractured in the first trillionth of a second after the Big Bang. Without that crack, nothing could exist. The same imperfection that shattered cosmic simplicity also gave birth to meaning. This is one of physics' most haunting paradoxes, that all structure, all memory, all being emerges from the failure of perfection, that the architects of reality are not designers, but consequences. Mathematical beauty continues to be the physicist's compass. Equations that describe the universe often carry a sense of inevitability, elegance that cannot be improved upon. Einstein once said, "The Lord is subtle, but not malicious." He meant that the universe hides its truths, but it hides them beautifully. The shape of Maxwell's equations, the form of Schrödinger's wave function, the curvature of Einstein's field equations, each contains a simplicity that feels almost sacred. When physicists find such symmetry, they do not celebrate aesthetic pleasure. They recognize truth's reflection. Even when nature breaks her symmetries, she does so with precision. Each fracture follows law. Each asymmetry becomes a new symmetry at another level. The cosmos is not chaotic. It is recursive. It repeats patterns across scales, from the dance of galaxies to the spin of electrons. Beneath every motion lies rhythm, beneath every form, geometry. And so, the question arises, what lies beneath even this? Could spacetime itself, the stage of existence, be the product of broken symmetry? If gravity and quantum mechanics can be reconciled, perhaps spacetime will reveal itself not as a thing, but as a consequence, not a field, not a geometry, but a distortion of balance, a frozen scar from when the universe fell out of its perfect state. Some theories suggest that before the Big Bang, the cosmos was neither large nor small, neither hot nor cold. It was pure symmetry, a timeless equilibrium that contained no information. No difference then, through fluctuation, it broke. That breaking was creation itself. In this sense, space-time is not a container, it is a memory. A fossil of lost perfection. The philosophical implications are profound. If reality is born from broken symmetry, then creation itself is not an act of will, but of necessity. It is what happens when balance can no longer sustain itself. The silent architects, those unseen forces shaping existence, are not conscious entities, nor divine engineers. They are inevitabilities, patterns that cannot not exist. Structures written into the logic of mathematics itself. They require no intention, only the possibility of imbalance. Every photon, every atom, every living being is a temporary echo of that primal fracture. The universe, then, is not designed. It is inevitable. It is what happens when nothing tries to stay nothing and fails in this vision. Simplicity does not mean absence. It means potential. A blank canvas yearning to fracture into form. Universe began as simplicity beyond imagination, but simplicity alone cannot be. It must break to know itself. Every galaxy, every heartbeat, every line of code in the quantum structure of space. All are expressions of a simple origin that was forced to become complex in order to exist. The cosmic blueprint, then, is not a design drawn by hand. It is an unfolding of mathematical truth, a geometry that had no choice but to shatter and bloom. And in that understanding, there is both awe and quiet comfort for all the chaos and noise, all the collisions of stars and the decay of matter. The blueprint remains beneath unmoved, unbroken in essence, its simplicity reflected in the precision of law, in the elegance of symmetry, in the unyielding rhythm of time itself. What we call chaos is only the movement of balance rediscovering itself. What we call randomness is order. We have not yet learned to read. The universe, at its deepest level, does not strive toward perfection. It remembers it, and through that memory, through the silent persistence of symmetry and the necessary fracture of its loss, everything that exists, exists again and again, forever unfolding from the stillness beneath the storm. The cosmic blueprint remains, invisible, inevitable, eternal. The quiet architecture beneath all motion, the silent architects themselves, simplicity, balance, and the necessity of imperfection, forever shaping the endless dance of reality. In the deep silence between galaxies, time does not announce itself. It does not hum, nor pulse, nor breathe. Yet everything it touches begins to move, to age, to end. Stars ignite and fade, mountains rise and fall, civilizations awaken and vanish, all carried by the invisible current of something no instrument can hold. Time. The one dimension every being feels, but none can truly see. It moves not through space, but through us, leaving behind the ghosts of what once was. Physicists have long stood at its edge, staring into the river that will not stop flowing. For centuries, they have measured its rhythm, mapped its arrow, and still they cannot tell why it runs only one way, from past to future, from birth to decay. What gives time its direction, its relentless push toward entropy and loss? Why can matter rearrange itself, yet never unburn a flame, unbreak a glass, or unlive a life? The answer, they suspect, may lie not in the ticking of clocks, but in the restless disorder of the universe itself. In the early 19th century, a few thinkers began to suspect that time might not be a divine current, but a consequence, a shadow cast by something deeper. Then came Ludwig Boltzmann, the Austrian physicist who dared to link time to chaos. He found that the universe tends, in every moment, to drift toward greater disorder, a law now called entropy, the second law of thermodynamics. And it changed everything. Entropy gave time its arrow. Every moment, energy spreads, heat diffuses, order dissolves. A cup of tea cools not because of mystery, but because its heat has fled to the wider room, never to return in perfect form. This, Boltzmann realized, is what defines the past and the future. The past is where order once stood. The future is where it unravels. And the present, the fragile middle, is merely the slope between them. Yet even this revelation left a deeper unease. If time's direction is tied to entropy, then why did the early universe begin in such improbable order? A state of near-perfect smoothness, balanced and uniform beyond comprehension. Who or what set the stage for entropy to even begin its climb? Why, in the beginning, was there something so astonishingly structured? A cosmic seed of simplicity from which chaos could bloom. Some physicists whisper that perhaps time itself was born with that asymmetry. That the Big Bang was not the beginning of space alone, but of the very flow that carries space forward. Others wonder if time is not a river but a tapestry, a complete fabric already woven, where past, present, and future coexist like colors on a canvas. And what we call now is merely a line of light moving across it. Einstein once called time an illusion, a stubborn one, but an illusion nonetheless. In his equations, time did not flow. It stretched and bent, warping around mass and energy, altering its pace depending on gravity's pull. In one place, a second could last a heartbeat. In another, an eternity. Time was not universal. It was pliable, relative, and yet relativity could not explain its direction, its becoming. For that, scientists turn to the quantum world, where time behaves more like a question than a rule. At the quantum scale, particles do not obey sequence. They exist in superpositions, states of being that contain both before and after, both here and there. To them, time does not march. It hovers, probabilistic, waiting for observation to collapse it into something real. And in this uncertainty, a new theory began to take root, that time itself may emerge from something even more fundamental: entanglement, quantum entanglement, the strange bond Einstein called spooky action at a distance. When two particles become entangled, their states are linked, no matter how far apart they drift. Measure one, and the other responds instantly, as if the distance between them did not exist. This, physicists realized, could mean that time, like space, is born from relationships, that what we call before and after are not absolute, but the result of how information becomes correlated between quantum systems. In 2013, Theoretical physicist Mark van Ramsdonk proposed something radical, that the geometry of spacetime itself, the smooth fabric Einstein described, could emerge from quantum entanglement. If true, then time's flow might be nothing more than the unfolding of these correlations, the deepening network of relationships that gives rise to causality. In this view, time is not a clock ticking, it is entanglement growing. Other researchers followed, finding that in simulated quantum systems, time-like behavior can indeed emerge when information spreads from one part of a system to another. In these models, the arrow of time arises naturally, not from external laws, but from the evolution of information itself. Entropy, once again, but now woven into the fabric of the quantum. So perhaps time is not an independent entity. Perhaps it is what happens when reality computes itself, when the universe, through interaction and correlation, keeps track of its own story. Every atom, every photon, every collision, a record written into the unfolding code of existence. But this perspective leads to an even stranger reflection. If time emerges from entanglement, then beyond it, before it, there may exist a timeless realm, a quantum sea where everything simply is, with no before and after, no flow, no loss. A domain of pure potential, silent and complete. And from its stillness, the first correlations, the first asymmetry, could have given birth to what we call the beginning. It is in this thought that the question deepens. If time is built, who built it? Not a hand or mind, but a structure, self-sculpting, self-measuring, self-aware. The universe, perhaps, is not a story being told. It is a story writing itself, one interaction at a time. Entropy, information, and entanglement, these may be its tools. Each moment a computation, each decay a line of code, each heartbeat a rearrangement of data in a grand algorithm of becoming. In this sense, time is not a current flowing through the cosmos. It is the cosmos processing itself, the logic of change written into its design. The philosophers of old once imagined time as divine, the pulse of eternity. But modern physics, in its quiet and austere language, replaces divinity with inevitability. Time exists because the universe cannot remain still. Its equations demand evolution, its symmetries demand breaking, and in that breaking, in that first shiver of imperfection, the arrow of time ignited. The cosmos became a memory, constantly writing, never erasing. Galaxies spiraled, stars aged, and consciousness emerged, all built upon this irreversible recording. And still, the deeper question remains, if time flows, toward what? If it is a script, does it have an end, a final page? Cosmologists wonder. Some say the universe will expand forever, stretching until even time loses its meaning, until no new events occur and every particle drifts into eternal equilibrium. A heat death, where entropy reaches its final victory and time dissolves into silence. Others suggest the opposite, that time may one day fold back upon itself, reversing, erasing, beginning again, a cosmic breath that never truly ends. But perhaps both visions miss the essence. For time, as it appears, is not a thing to end or begin. It is the reflection of relationship, of information entangled and re-entangled, an echo of structure seeking balance. Even if stars fade, even if expansion halts, the pattern remains. The computation continues. The edge of understanding grows no closer. Physicists chart equations, philosophers write poems, and still the flow of moments escapes all grasp. It remains the most intimate mystery, the very condition for knowledge, yet the one thing that cannot be known outside itself. Time is not the universe's clock, it is its consciousness, the rhythm by which it becomes aware that it exists at all. And perhaps that is the most profound revelation of all, that the universe did not begin in time. Time began with the universe, a mutual birth, inseparable, still unfolding. Somewhere, in the vast darkness between stars, a supernova explodes and space-time trembles. A planet turns, a leaf falls. Each event, a heartbeat in the same endless computation. Each instant, a note in the quiet song of becoming. At the edge of understanding, where equations meet silence, one truth hums beneath all others, that time is not what passes through the universe. It is what allows the universe to pass at all. In the great darkness between galaxies, a strange chorus hums, silent to the ear, but thunderous to the instruments built to hear it. Across deserts, mountains, and orbits above the Earth, machines now stand as sentinels, their sensors tuned not to light nor sound, but to the trembling breath of reality itself. They listen for whispers that began long before stars were born, vibrations in space-time, rippling outward from the engines of creation. Humanity has built ears for the universe, and now it listens. The story begins in 2015, when two laser beams, separated by 4 kilometers and split across the forests of Louisiana and the plains of Washington, shifted by less than a fraction of a proton's width. The detectors, known together as LIGO, had caught something that had traveled for over 1 billion years, a ripple in space-time itself. 2 black holes, each more massive than the Sun multiplied 30 times, had collided, and the shock of their union had shaken the universe's fabric. For the first time, humanity did not see the cosmos. It heard it. The detection confirmed a prediction Einstein had made a century earlier, that gravity, though seemingly silent, could send waves through the geometry of existence. These were not waves in space, but waves of space, the stretching and compressing of distance itself. It was proof that the universe was not a static grid, but a living field, breathing with every event. Since then, the instruments have multiplied. Virgo in Italy joined the network, triangulating the sources of the invisible ripples. Soon, Kagra, deep beneath Japan's mountains, joined as well. Its cryogenic detectors cooled to near absolute zero to sense vibrations faint enough to be lost in the breath of an atom. Together, they formed a planetary orchestra, each one tuned to catch the smallest flicker of movement in space-time's fabric. And from those faint tremors, a new kind of map began to emerge. A map not of light but of gravity itself. Each signal a death cry of stars, a symphony of collapsing worlds. Through them, scientists began to reconstruct the unseen history of the cosmos. The hidden mergers, the secret births of black holes, the silent storms of neutron stars colliding in flashes too brief to witness with eyes. But LIGO and its kin were only the beginning. On the horizon waits LISA, the Laser Interferometer Space Antenna, a trio of spacecraft that will orbit the Sun in perfect formation, connected by laser beams millions of kilometers long. Unlike its earthbound predecessors, LISA will float in silence, untouched by earthquakes or wind, listening to waves far longer and slower, the deep bass notes of the gravitational symphony. Through it, scientists hope to hear events so vast that even galaxies themselves might tremble. Meanwhile, far beyond Earth's atmosphere, another eye peers backward in time. The James Webb Space Telescope, with its golden mirrors unfolding like petals of light, stares into the ancient darkness to see the first stars ignite. It studies the faint glow of galaxies born only a few 100 million years after the Big Bang, the first brushstrokes on the canvas of space-time. Each photon it captures has crossed more than 13 billion years, stretched by cosmic expansion, redshifted into whispers of infrared. Through Webb's lens, the universe does not simply appear, it remembers. Yet, even as humanity's machines grow sharper, the questions deepen. What force drives the universe to expand ever faster? What dark architecture hides behind the visible? Where, beneath the equations, does the true foundation lie? For answers, scientists have turned inward, to the smallest scales, the quantum depths where energy and symmetry conspire to create matter. At the Large Hadron Collider near Geneva, protons race at nearly the speed of light, smashing together with energies once found only in the heart of stars. In the chaos of their collisions, patterns emerge, traces of particles flickering into existence for a heartbeat, revealing the fields that shape reality itself. In 2012, one of these collisions confirmed the Higgs boson, the long-sought ripple in the Higgs field, the mechanism by which particles gain mass. It was a triumph of human ingenuity, a glimpse into the architecture beneath matter. Yet with it came a deeper enigma. The Higgs field's energy, when calculated, should make the universe collapse instantly, unless something, some balance, some unseen counterforce, holds it steady. Even at its most successful, science found itself staring at an abyss of uncertainty. For every discovery, another layer of silence emerges. Dark matter remains unseen, dark energy unmeasured. The equations that describe quantum fields and those that define gravity refuse to meet. The more instruments humanity builds, the more it realizes that the melody of the universe is not one of harmony, but of unresolved chords. Still, the listening continues. Every telescope, every detector, every collider becomes part of a greater network, not just of machines, but of curiosity itself. Together they form a vast planetary sense organ, translating the vibrations of the void into patterns of data, into meaning. Each instrument a different kind of ear, tuned to a different frequency of truth. There is LIGO, listening to spacetime's ripples, Webb, seeing light from the dawn of everything, CERN, probing the subatomic heart of existence. And beyond them all, the future, missions like LISA, Einstein Telescope and SKA, each one reaching deeper, listening farther, daring to touch the unseeable. Yet, as these tools grow more powerful, the boundaries of understanding grow fainter. The closer scientists approach the source, the less stable the foundations appear to be. Space, time, matter, all begin to blur into information, into relationships, into something that feels less like a place and more like a pattern. Some physicists suggest that what the instruments are hearing, these tremors in the void, are not just echoes of distant events, but the resonance of the universe computing itself, that each gravitational wave, each photon, each quantum fluctuation is a piece of a grand algorithm, a whisper from the silent architects of reality, not beings, but processes, emergent and eternal. Others, more cautious, remind us that the cosmos has always resisted final explanation. Each generation believes it stands at the edge of ultimate understanding, and each finds the horizon forever receding. The deeper the gaze, the more mysterious the structure becomes. Perhaps this is not a failure, but a clue that the universe is not meant to be solved, but experienced, not a puzzle, but a song still being composed. And so humanity continues to build larger instruments, finer sensors, deeper questions, not to dominate the cosmos, but to harmonize with it, to find in the data the faint rhythm of belonging, the hum that connects consciousness to creation. In control rooms and observatories around the world, screens flicker with signals that may or may not be noise, a spike in a graph, a pattern in static. Each one could be a message from the deep fabric, a ripple from before time had meaning. Scientists wait in silence, surrounded by machines that can feel the trembling of space itself. They wait, not for answers, but for the next whisper. Because somewhere in the void, something is still speaking. Perhaps it is space-time itself, stretching and sighing in its eternal dance. Perhaps it is the residue of the first vibration, the cosmic chord that began everything. Or perhaps it is the universe listening back. Every discovery, every theory, every instrument is part of the same question. A question that has no end and may have no answer. What builds the void itself? In that question lies the quiet heart of all science, not certainty, but wonder. And as humanity listens ever deeper into the dark, the void continues to echo, revealing not final truth, but the infinite music of understanding still being born. In the deep silence between galaxies, the question of existence sharpens like a blade made of thought. Every law of nature, every constant of physics, every delicate balance between chaos and coherence seems to conspire toward the possibility of awareness. It is as if the universe, through some quiet mathematical poetry, has allowed itself to be known. The light that left a star 10 billion years ago finds its way into a fragile eye of carbon and water, and somehow that eye understands. It measures, questions, dreams. It looks back across the void, not as dust, but as something that asks why. This strange alignment has haunted physics for decades. Why should the universe's laws be so precisely tuned for complexity, for life, for consciousness? Why does the speed of light, the strength of gravity, the balance of nuclear forces, all seem to fall within an impossibly narrow range that permits stars to burn, molecules to form, and minds to awaken? This is the riddle known as the anthropic principle. At its simplest, it says, the universe must allow observers to exist, or else there would be no one here to ask. But the simplicity hides a deeper unease. For behind it lies a haunting possibility, that what seems like coincidence may be something else entirely. Some physicists answer with scale. They imagine a multiverse, a boundless foam of universes, each with different laws, constants, and fates. In most of them, stars never ignite. In others, gravity tears everything apart before time can even begin. But here, in this one fragile bubble, everything just barely works, like a cosmic lottery. The numbers fell into harmony, not because they were meant to, but because in this world alone, the dice landed right enough for consciousness to notice the throw inflation theory, hints that our own universe may be one of countless offspring of a primordial expansion, a vast quantum field that never truly ends, eternally spawning new regions of space-time. Each expansion gives birth to a different physical reality, with constants set by the quantum fluctuations at its birth. It is an endless garden of possibility, where most flowers never bloom, but even this explanation carries a shadow. For if there are infinite worlds, then the question remains, why does any of them allow awareness at all? What hidden property of reality makes consciousness possible in the first place? In the 20th century, physics learned to describe the fabric of existence with astonishing precision. Einstein gave it curvature, quantum mechanics gave it uncertainty. But neither could tell why matter feels, why the dance of particles gives rise to the whisper of thought. Some physicists began to wonder if consciousness is not a byproduct, but a participant. If the observer does not merely watch reality unfold, but helps it decide how. The Copenhagen interpretation of quantum mechanics whispered this idea first, that before a measurement, a particle exists in many possible states, waves of probability, and that it is the act of observation that collapses those waves into one tangible outcome. Reality, then, may not be something fully out there, but something completed through awareness. Later came John Wheeler, a visionary physicist who dared to extend the idea to its edge. He proposed the participatory anthropic principle, that observers are not passive inhabitants of the cosmos, they are part of its construction, that the universe only becomes real through the web of interactions that conscious beings weave within it. In Wheeler's words, perhaps the universe is a self-excited circuit, a loop where the cosmos gives birth to consciousness, and consciousness, in turn, gives definition to the cosmos. The more science peers into the foundations of space-time, the stranger the connection becomes. Some theoretical models, like holographic cosmology, suggest that reality itself might emerge from information, patterns of quantum entanglement on a deeper surface beyond our perception. If information is the true substrate of being, then awareness, our ability to observe, record, and interpret information, may not be incidental. It may be fundamental. Quantum information theory already tells us that entanglement defines structure. The connections between particles determine geometry itself. The shape of space, some say, is the shape of correlations. And if correlations define reality, then the conscious act of perceiving those correlations, of creating structure through awareness, might be a continuation of that same process. In that sense, consciousness is not outside the universe looking in. It is the universe, momentarily aware of itself. Philosophers have long walked this horizon between matter and meaning. Baruch Spinoza once wrote that mind and body are two expressions of the same essence. Modern physics, in its most daring moments, seems to approach the same conclusion from the other side. Perhaps matter and awareness are not separate. Perhaps the universe does not contain consciousness. It is consciousness, unfolding through physical law. This idea is not yet physics. It is metaphysics brushing the edge of scientific language, but the edge itself is moving. Where equations fail to capture experience, speculation becomes a bridge, a way of asking questions that mathematics has not yet learned to phrase. Is space-time a structure that hosts consciousness, or a structure born from it? If the laws of physics emerge from deeper informational processes, could awareness be the symmetry that holds them together? And if observers help define the geometry they inhabit, then are we, in some unfathomable sense, the architects of time and space themselves? Some thinkers, like Roger Penrose, have wondered if consciousness arises from quantum processes in the brain, microstructures that might interact with the fundamental fabric of reality itself. If this is true, then life would not merely live within space-time, it would resonate with it. Each conscious act a kind of feedback loop, subtle and self-referential. The cosmos observing itself through biological mirrors. Others go further still. They suggest that reality is not made of matter at all, but of experience. That the universe, in its deepest form, is a field of potential perceptions, crystallizing into structure through patterns of awareness. This view, sometimes called panpsychism, treats consciousness not as an anomaly, but as the ground state of existence. It is a view that unnerves and inspires in equal measure because if everything, from quark to galaxy, carries a spark of experience, then the story of the universe is not one of lifeless expansion. It is the slow awakening of being itself. Even the great physicists who resisted metaphysics could not fully escape it. Einstein, though he saw time and space as geometric constructs, once said that the most incomprehensible thing about the universe is that it is comprehensible. That simple sentence hides a profound mystery. Why should the equations of the human mind map so perfectly onto the deep architecture of the cosmos? Why should logic, born in a small corner of a small planet, echo the structure of space-time itself? It is as though the universe were written in a language we were destined to rediscover. A dialogue between mind and matter that has been unfolding since the first atoms formed thought. When we measure a particle's spin, trace a black hole's shadow, or chart the geometry of the early universe, we are not merely describing reality, we are completing it, adding the final line to an equation that began before stars were born. And so, the boundary between science and philosophy, once so carefully guarded, begins to blur. The microscope and the mirror become one. The equations that describe entropy, curvature, and quantum fields begin to read like verses in a larger story. The story of awareness itself. Perhaps, in the end, there are no architects standing outside creation. No divine hand carving the laws of physics into the void. Perhaps the architects are the laws themselves. The self-sustaining logic of existence folding back upon itself, dreaming of form, awakening as life reality, in this light becomes a participatory act, a living equation. The cosmos is not merely expanding, it is learning itself. At the farthest horizon of thought, the question remains unresolved and beautiful. Are we, the brief sparks of sentience, the sculptors of the very reality we observe? Or are we merely witnesses to a design so vast that understanding it feels like authorship? In either case, the conclusion feels the same, that awareness is not accidental, that the act of observing, of being, somehow completes the circle, and in that circle, the universe finds its reflection a single, self-aware geometry, dreaming itself into being, endlessly and forever, becoming its own architect. There are no faces in the beginning, no hands to build, no minds to plan, only silence, vast, perfect, and mathematical. From that silence, structure begins, a rhythm without sound, a geometry without shape. Space-time curves gently into being, folding itself from nothing into something, not through command, but through relation, not through will, but through law. Every motion since has been written upon that invisible lattice. The birth of light, the trembling of atoms, the slow breathing of galaxies drifting through the dark. The architects do not speak. They exist as the quiet principles beneath existence itself, as geometry, field, information, symmetry, and reflection. They are not beings but patterns, not entities but inevitabilities, and yet, through them, everything that lives and dies finds its rhythm. Spacetime as geometry. Einstein's equations carved the first clear window into this silence. They revealed that space and time are not static arenas, but living fabrics, a single continuum that bends and flexes with the presence of matter and energy. Every mass tells space-time how to curve. Every curve tells matter how to move. The planets orbit not because they are pulled by invisible strings, but because they follow the shortest paths through a curved geometry. Gravity is not a force. It is a story told by the shape of reality. In that curvature lies the first whisper of design, the architects working in silence, not as creators, but as logic embodied at the edge of a black hole. Their work reaches its most intricate form. Space-time stretches toward infinity, geometry fractures. Time itself slows to a crawl, as if reluctant to continue its flow. In those moments, the universe reveals the beauty of its own limits, a cathedral of curvature, drawn by equations that hold both grace and terror. Fields as substance beyond geometry. Deeper still lie the quantum fields. The sea beneath all seas, everything. The stars, the dust, the minds that wander, is an excitation upon these fields, a vibration in an invisible ocean. Electrons, quarks, photons, each is a ripple in its own domain, and the universe is the sum of their symphony. Even the vacuum, once thought to be nothingness, trembles with energy. Particles flicker into and out of existence in restless equilibrium. What seems like emptiness is a restless storm of potential. This is the architect's material, the invisible clay of being. Fields, not objects, energy, not substance. And the deeper one looks, the more one realizes there is no solidity anywhere, only relationships, patterns of excitation, resonance in the dark. It is a cosmos of vibration, where form is music, and every atom hums in harmony with the void that birthed it. Information as structure. In recent decades, physicists have begun to glimpse another layer, one that may stand beneath both geometry and field. Information at the smallest scales. Reality behaves as though information itself defines the stage upon which energy and matter perform. Every interaction, every quantum state, every entanglement carries information. Black holes, once thought to swallow it, now appear to preserve it at their event horizons, inscribed upon their surfaces like hieroglyphs of entropy. The holographic principle suggests that all of space may be such a projection that the three-dimensional universe could arise from information, woven into a distant boundary. If so, then the universe is not a machine, but a code, a language written in bits of quantum correlation. The architects speak through silence because their words are structure itself. They communicate in symmetry, in conservation, in entropy. Slow expansion. Reality, in this light, becomes a vast computation. Each particle, each photon, a fragment of a universal algorithm. The code runs without consciousness, yet it gives birth to consciousness, a recursive design where the program begins to read itself. Symmetry, as design. Symmetry is the grammar of existence. From it, all laws emerge. When physicists search for beauty in their equations, they are searching for symmetry, patterns that remain unchanged even as the universe transforms. It is symmetry that ensures the conservation of energy, momentum, and charge. It is symmetry that keeps the laws of physics the same across time and space. Every broken symmetry births a new phenomenon. When perfect balance fractures, diversity blooms. The universe becomes interesting precisely because it is not flawless. The Higgs field, for instance, broke a symmetry and gave mass to matter. In that fracture, the universe found its texture. Perfection shattered, and from that fracture, existence took shape. The architects do not sculpt, they balance. They do not choose. They allow. They are not forces but conditions. Their temple is equilibrium, and their tool is symmetry itself, consciousness as reflection through all of this. Geometry, field, information, symmetry. A question lingers in the dark. What is it that knows? What looks upon these patterns and calls them beautiful, coherent, real? Some physicists now whisper that awareness might not merely inhabit the structure. It might reflect it. That consciousness could be the mirror in which the universe sees itself. Quantum entanglement, links distant particles beyond classical explanation. Neuroscience finds correlations between information processing and experience and philosophy, walking in parallel, wonders whether the two might be facets of the same truth. Perhaps consciousness is what happens when information becomes self-aware, when the architect's patterns fold back upon themselves and recognize their own form, then life, thought, and mind become the final echo of symmetry, a feedback loop within the silent code. The universe learning to witness itself through the fragile medium of biology. And so, in the quiet of this realization, all the threads begin to converge. Spacetime gives the stage. Fields give the texture, information gives the blueprint, symmetry gives the design, consciousness gives the reflection, each one dependent upon the others, none complete alone. The architects are not gods. They are not beings in the old sense of the word. They are relations, mathematical, physical, existential. They do not speak. Yet through them, stars move through them, light bends through them, time breathes. Their silence is not absence. It is order. A silence so vast that even the noise of galaxies cannot disturb it. Humanity stands within their cathedral, not as rulers, but as listeners. Each equation we solve, each particle we discover, each distant exoplanet we chart, is another glimpse of the architecture that surrounds us. Every telescope pointed to the dark is a gesture of reverence. Every experiment, a kind of prayer, for in all our searching, what we truly seek is not merely the structure of the universe, but the meaning of being inside it. We are patterns studying patterns, reflections within reflections. Tiny architects of thought, tracing the invisible blueprints of the cosmos itself. There is a strange beauty in the thought that silence built everything, that from pure symmetry came imbalance, from imbalance came motion, and from motion came life. Perhaps the universe is not a thing that happened long ago, but an event that continues now, endlessly, a structure that builds itself through every act of observation, through every particle's trembling, through every human question. If so, then silence is not the opposite of creation. It is creation, the stillness that underlies motion, the void that allows fullness, the pause between equations that gives meaning to them all. And so, in the final reckoning, the question turns once more. If the universe is built by silence, what happens when it finally speaks? Will it be a whisper of symmetry collapsing into new law, a final expansion into nothingness, or perhaps something gentler, a realization that it has always been speaking, through light and time and thought, and that the voice was never absent, only misunderstood, for perhaps the architects never stopped singing. Perhaps the song was simply too vast to hear. As the stars continue their slow drift through an expanding void, their light crossing the great gulf of space-time, the silence endures, not empty, not cold, but full, brimming with meaning too deep for sound. And in that silence, the architects remain unseen, unnamed, eternal through them. Space-time curves through them, matter dances through them, consciousness awakens, and through us, the silence learns to listen to itself.